Drawings, remember Simon sat in his bathtub, does drawings. Anyway, that I can't, yeah, I'm dating myself again. Saturday Night Live from the late 80s. Okay. 24 is history. It's toast. We've done it. We have finished chapter 24. We're now going to do chapter 25 today. And you guys have already kind of done 25 because you guys were doing lenses and doing the lens equation. The mirror equation is the same thing as the lens equation. Okay? It's the exact same thing. But you kind of got to need to know how mirrors work. Okay? So that's what we're going to do today. We're going to learn how mirrors work. And it's pretty quick. It's not too bad. It actually goes pretty fast. Do I have any? Does my electromagnetic wave that's supposed to be tuned to the same frequency as that switch work? No. Okay, there it goes. All right. All right. And today we'll do some more good parenting skills thing for like when your kid asks the question, why does this on the passenger side mirror, why does it say objects may appear closer than they are? No, further away. Right. Objects in the mirror are actually closer to you than they appear in the mirror. We're going to find out why. Mainly because it's a convex mirror. Okay? That's why. It's a convex mirror so that you always, no matter where the object is, that mirror is convex so that you always get an image that is virtual and upright. Okay? Because that would probably screw you up a little bit if all of a sudden the semi behind you is upside down. It'd kind of disorient you a little bit, possibly. All right? So, let's talk about mirrors. The mirror equations, and then I want to go out for a nice run in this weather. So we're going to be done at 12:21. No, I'm kidding. Well, I'll make sure that we understand it. But all the rest of you are going, oh, please, can we get out of here at 12:21? Please, we won't tell. Okay. All right, here we go. Chapter 25, and away. Uh-oh. Ruh-roh, this doesn't look good. I could have sworn I saved chapter 25 over here. Oh, here it is. Scare me. All right. And we will slideshow. Okay. Slideshow from beginning. Ta-da! Reflection of light. Mirrors. Oh, fine. There. Get this out of the way. All right. Reflection of light and mirrors. Here we go. Ta-da! All right, now this is where they're using, like I've said, the great disservice that we do to you all is that we don't teach you about sound, okay, which are the first waves that you learn about. But there's so much involved with sound that it would, I don't even get to thermodynamics really, so, because there's just too much to cover. Just a public service announcement or a defense on my part. Back in the day when I went to college to learn physics, it was spread over 3 semesters instead of 2. So you got like mechanics, then you got temperature, thermodynamics, sound, all that stuff. Then you got electricity and magnetism at the end, so that we could cover. And you kind of covered a little bit of electricity and magnetism. Then you got into light and all that kind of stuff. But anyway, then they thought, oh no, we can just tell them, not really teach them, but just show them the material and say we taught it, and condense it down to 2 semesters. Okay. Because the problem is, if you guys, think about it, if you guys only needed 8 hours of physics for your pre-farm, how many of you would take that 3rd semester? Okay, there you go. All right, so anyway, got these wavefronts, boom, pulsating out, and if I get far enough, what they're trying to show you is if, like right at the front, it's curved, it's a curved plane that they're coming out of, but as I get further and further away, it becomes a plane front. It's not a curved wavefront anymore. It's a nice flat plane wavefront. This is all just a little bit of background information. Here is chapter 25 and 26. This is where we start. Okay? the incident ray, that's the ray coming in, light ray going boink. Think of it for right now as, well, anything, any kind of ray that comes in there and bonks it will be fine. Okay, the normal line is what's coming up off the surface. That's the perpendicular to the surface, the normal. Okay, and here's the deal. Theta I, theta of incidence, is equal to theta of reflection. Did they teach you that in your lab? No, they just assumed you knew it already because you're supposed to. Okay. Right. Okay, so theta I is equal to theta R. That's the big deal here. Okay, in chapter 26, what we're going to do is we're going to get away from mirrors, and we're going to go to where actually the light passes through, and it will have angles of what we call refraction. But the angle of incidence equals the angle of reflection, and that is taken off the normal. Okay, it is taken off the normal. So just say theta I equals theta R every time. Okay? Now, if you have, back in Galileo's day, when he was always messing with his lenses and stuff on his telescopes, and even today, what they do is a very, very expensive piece of optic equipment has been polished and polished and polished and polished and polished and polished. Why? Because then you get a nice, as they call it, specular reflection, or spectacular. No, it's actually specular reflection. Because see, all the rate, in other words, you'll get a nice image coming off of something like this. Whereas this is like funhouse mirrors, right? Where it looks all goofy and everything. Because, or you get kind of like somebody's, if this was actually the ray that's coming, the reflection of their toe or something like that, now it's all of a sudden where their belly button's supposed to be, things like that, you get Van Gogh. But anyway, so that's why they polish and polish and polish mirrors for, and lenses to get good resolution. All right. And notice, parallel incident rays coming in are going to have parallel coming out. Optics is wonderful because it's just good old 9th, 10th grade high school geometry. It's great. It's great. Okay. Now we do know about this, and we know about insumobles. Right? If you look at it, so it's in the mirror that it says ambulance. All right. Okay. Okay. Now, anyway, all right. The image has three properties for a plane mirror. This is for a plane mirror. We're going to spend most of our time today discussing spherical mirrors because that gets us ready for the mirror equation and also the lens equation for chapter 26. The image has three properties. It's upright, it is the same size as you are, and the image is as far behind the mirror, behind the I don't know what they're trying. What are they even trying to?
Distance M, I think.
Exactly, behind the mirror M that you are in front of it. In other words, if I'm about, what would you say? That's about a free throw, a little bit more. 6 meters. I'm about the 3-point line, I guess. 6 meters from the wall. Okay, so my image would also be 6 meters behind. And it'd be the same height that wall sees me. Okay? Which is kind of weird, if you think about it. Because like, Jared, you're about twice the size of my thumb. So you're only this tall. That's the image that I see. It's kind of, you got to keep that in mind. So when they say an image is so high, or Marcus, sorry about that. I was looking at Jared and Marcus. Okay. All right. Now what is it with strep throat this summer? I had 2 of you go down with it, and my daughter had a bunch of, she's teaching summer school, a bunch of her teacher friends got it too. Didn't your parents get your tonsils taken out when you were little? What's that? It's not required? You know why? Because pediatricians want that repeat business. That's why. My ear, nose, and throat cousin, who's a doctor in ear, nose, and throat, says that's the only reason pediatricians tell kids not to get their tonsils out, parents. It's because they want repeat business. But he was being a little facetious, but there's some truth to it, I think. All right, anyway. Well, it's also, you know, the whole surgery thing is scary. Okay. All right, but anyway. Okay, a ray of light from the top of the chest. Okay, here's how it works. Here's a third of incidence equals a third of reflection. And so you get this dotted line anytime, from now on, anytime you see an image formed by dotted lines. See, so they basically what they did was they took this right here, shot it over here, this one right here, came back here and got this image. Anytime you see dotted lines from now on, that's a virtual image. It's not a real image. It's a virtual image. And a strange thing that we're going to find out, and last summer I broke the mirror, but luckily Dr. Roble was happy about it because he hated that mirror, and we got a prettier one. We got a nicer one, a nice spherical mirror. One of the weird things that happens that we don't see very often in our everyday existence is you can actually get what is known as a real image in front of a mirror. Okay? It actually happens. In other words, due to, you know, it won't happen in a plane mirror, okay? But when we get to concave mirrors, you can set up a box with a flower on top of it. Then all of a sudden, it looks like the flower is actually upside down and closer to you than the mirror is, which is kind of a weird thing. For those of you who have depth perception, I have no depth perception. I look at everything with one eye, so it kept me out of flight school. But bumpy landings. Okay, the Marines didn't want people flying helicopters that had no depth perception. That could be. Well, I thought I was on the ground. Get out, boys. All right. Okay, now here we go. Yep, as you can see, as a plane mirror, the distance of the object is the same as the distance of the image. All right, and they do a bunch of little geometry there just to show you. All right, it's inverted though. Okay, I hate this thing, so we're going to move on. Basically, what it's saying is this. Here it is, and I'm not going to go through it because every time I go through it, I get stuck, and then I flail around, and people just get confused. Just take my word for it. To get a full-length image, all you need is something that's half the height. Okay? And you can, there, the optics pros in the back are saying, yeah, that's all you need. Just need to get a full-length image. In other words, if I need a full-length image of myself, all I need is a mirror that's half my height. Okay? Now I have to stand an appropriate distance away behind it. You know, but actually, if you had a mirror this big and stood way far away from it, you couldn't see anything in it, but you could get your whole image in there possibly. Okay? But anyway, you just need one that's about half your height. Oh, and this is fun. This will be on the test, I guarantee you, just because it's kind of cool. All right? That if you have two, now what they've done is, all they have are two mirrors at 90 degrees here. Okay? It looks like they've got like full, you know, 4 mirrors there sliced into each other. But actually all they have is 2 mirrors that are at 90-degree angles. Okay? And look, they've come up with 3 images, which is kind of cool. You get the left side of her face here, the image. You get the right side of her face over here, and then you get them both right there. But actually, this is her left, that's her left, her right, that's her right. It's kind of strange. But, so you can do all kinds. Any of you seen the old Man with the Golden Gun? James Bond? He's trying to find the, oh well. He's in a house of mirrors. And the little midget guy from Fantasy Island was in it. Never saw it? Okay. All right. Nobody saw that 1977 James Bond episode. Okay. Now, let's talk about spherical mirrors. Here we go. Now we're ready to talk about good old spherical mirrors. Oh! The big thing that we've known so far is the angle of incidence equals the angle of reflection. Angle of incidence equals angle of reflection. Okay. Now it says if the inside surface of the spherical mirror is polished, it is a concave mirror. In other words, if it's caved in, all right, if the world is out here, okay, that's the other weird thing about mirrors. You've got this whole virtual world that lives behind them, okay? And that's Lewis Carroll. You all know Lewis Carroll? Okay, through the looking glass and all that stuff. Lewis Carroll is actually a top flight mathematician. And that was his flight of fantasy, was to write the whole Alice in Wonderland thing. But, you know, he got to thinking in mathematics in the different dimensions and working with mirrors and the lens equations and stuff and going, ooh, there's a whole virtual world on the other side of ours. I wonder if we could get in there, what it would be like. Those kinds of things. Okay. Well, anyway, so there you got a little history too. And actually, Queen Victoria, when he wrote Alice in Wonderland, Queen Victoria really liked his book. And so she said, can I be the first one to get the copy of your second book? He said, sure. And it was some treatise on mathematics, you know, some book on upper level topology, and said, here you go. I don't know if she read that, but anyway. All right. She was not amused. Sorry. Okay, now, the law of reflection applies, so it is just as it does for a plane mirror. The principal axis of the mirror is a straight line drawn through the center and the midpoint of the mirror. Okay? So right here, it's your principal axis. Now C represents what is known as your radius of curvature. R is your radius of curvature, okay, of the mirror. R is your radius of curvature. Okay? Now then, notice what we've got here. We've got a concave mirror. We've got this tree out here, all right? And then we get these things, these rays coming out like this. And we wind up with an image right here. Now, are those ray lines that we've drawn there, are they dotted or are they solid red lines? Solid red. So that means we have a real image, okay? Which is kind of weird, okay? So if we were like behind this tree or even in front of it, we'd think this tree, if we were like standing here, we'd think, oh, this tree's right here. It's kind of weird. All right. Depending on where we were standing. Whoops. Okay. Principal axis. The focal length. This guy is huge too. You've seen this little F. Didn't you see that in your lab? The left, focal length. Had no idea what it was talking about. Focal length is 1/2 of the radius of curvature. Okay? Focal length is 1/2 of the radius of curvature. That's probably in the next slide. But but the main thing is, with a concave mirror, the focal length is positive. With a convex mirror, guess what? Convex mirror is when I flip this guy over. But my world is still out here, and we've got this virtual world behind it over here. When I flip this guy over, now my focal length becomes negative. Okay? So my focal length is negative for a convex mirror. Okay, there's the main thing. Focal length equals 1/2 R. All right, and here's a little geometry to show it, because basically what they're doing here is this radius, this line that's R, the radius of curvature, becomes, okay, it is normal to the mirror. Okay, so this line is normal to the mirror. So a line coming in here and then bonking out like this is, angle of incidence equals angle of reflection. So it comes back this way. But notice what happens. Since this line is parallel to this line, we've got alternate interior angles. So therefore, these two angles are the same. So if you have two angles like that, what do you have? You have an isosceles triangle. Okay? And so this isosceles triangle, so this side is the same as this side over here. And Boom. The focal length is at 1/2 r. Cool little geometric argument for that based on the laws of physics of what incidence of angle of incidence equals angle of reflection. I have to be careful and not say refraction. All right? Okay, now notice what happens. The focal length, only a few of the lines, only a few of these parallel rays here bring the ray into, go right through that focal point, okay? That's the nature of spherical mirrors. You get this aberration type thing, okay? In other words, it's very diffuse. It's diffused out. However, if I have a parabolic mirror, which might be the next picture, yes. This is a parabolic mirror. Now what this is doing is this is used to heat this oil in here, or to heat the water in there. This is not a spherical mirror. These are parabolic mirrors. Y'all remember, you might have done it, it might have been a more advanced, an extra credit type problem that you did in Algebra 2 or in advanced math or pre-calculus class. You figure out that there is a point where all angle of incidence goes through the same point of a parabola. And so all the rays of the sun that are getting reflected right into this point right here. So it makes it very, very intense, high intensity. Okay? It makes it very hot, heats it up. Which that's kind of cool too. Okay. Now, here we go. Now when we flip the mirror over, again, here's our real world. Here's our little virtual world behind the mirror. But notice, when the mirror's flipped over, now we've got this angle of curvature or this radius of curvature is now in the virtual world, and so the focal length is now negative 1/2 r. Okay? One is now negative 1/2 r. Okay, now, concave mirrors. We do not have the time in summer school, and a lot of times even in the fall and winter semesters, I don't have time to do the ray diagrams. But I think they're kind of important to at least see, okay? This is what you do in an optics lab. And in fact, every other winter, an optics lab is offered, taught by Dr. Kruger, the chair. He's a big optics guy. And anybody who's had 220 can go ahead and take it. So if you want to take an extra, if you're working on your minor in physics and you want to take that optics lab, it won't be offered this winter, but the winter after next. And most of you are going, I'm out of here next winter anyway. Sayonara. Okay, so, but anyway, if you're still around the winter and you need 3 hours of science or something, he's opened that up to all comers. It's like Physics 420, I think. Sounds scary, but it's not. Well, it kind of is. Because it's an optics lab. But it's a lab with a real full professor. Has that ever happened to you all before? No. Okay. And not yet, anyway. It will when you get to grad school or medical school, hopefully. All right. Anyway, so this is where you do a ray diagram to get. Here's our object. So the first thing you do is you draw a straight line. You draw a straight line like this, point that goes, then reflects back through the focal point, okay? Then you draw line number 2 that goes through the focal point and comes back this way. And then the third line you draw comes from the mirror. Now, this ray right here, since it is parallel to the radius of curvature, really, since it's parallel to the radius of curvature, the angle of reflection is going to come right back this way and come back here. So when I put all these together, you can probably see what's going to happen. When I put all 3 of those ray diagrams together, you only need 2, really, to find out where your image is going to be. I wind up with an image that is real because it's in my real world. It's on this side of the mirror, okay? And it's upside down. So if I'm looking at this thing here, I've got a real image that's upside down from the regular object. And it's like right in front of me. It's kind of strange. A spoon. Yes, y'all ever been bored at the dinner table playing with the spoon? Same thing. All right. Exactly. I keep meaning to remember that thing. All right. And then, notice now, we've moved the object this time to where the image was, and now I've got a real image that's upright, and it's between that. And my image is now between the radius of curvature and the focal length. Okay? Okay, now, so, notice with a concave mirror, we can get an image that is real and inverted. We can get an image that is real and upright. And we can also get an image that is virtual. This is the way a makeup mirror works. In other words, a makeup mirror has a really large radius of curvature. It's a concave mirror with a very large radius of curvature. You might not even be able to tell it's so large that it actually does have a little bow to it. Okay? And what that means is your face, or whatever, the object is between the focal length and the mirror. And when the object is between the focal length and the mirror, that blows it up bigger here, okay, on the back side of the mirror. All right, so makeup mirror, in other words, it's magnifying her. Okay? All right. And it's a virtual image, but it's upright. We wouldn't want a makeup mirror like a spoon. All of a sudden we're trying to, put on our eyeliner. I hate it when I put on my eyeliner and I go upside down. All right. When I'm getting ready for Rocky Horror. No. Okay. All right. This has always confused me, so we'll move on. All right, now. Here we go, convex mirrors. Now we're going to talk about convex mirrors. Okay? And again, what they do is, got the object, and we're going to go through, here's the object, and we're going to go through the ray diagram. So we've got this one that comes here. Oh, look at that angle of incidence. Here would be the normal to it. So the angle of incidence equals the angle of reflection, goes shooting way off here. And then we go from the top, and we go right through the, we're trying to draw a line straight for the focal length here, okay? And so that line right here reflects back this way. And then we've got this one that's going to go right through the radius of curvature, and it comes back this way. So these three virtual lines come down here, and we get an image that's virtual. So here's the deal. Convex mirrors are always, the image is always shrunk and upright and virtual. Three things. It's smaller, it's upright, and it's virtual. Every single time. So here's, actually, the guy I played football with at Liberty High School. Well, actually, I didn't play football. I watched the other guy. I wore a uniform and watched the other guys play football. But a friend of mine who actually did play football became a Blue Angel. This is a picture of the Blue Angels. He went to West Point, hated it. Then he went to Northwest Missouri State and went to Naval flight school after he graduated and became a Blue Angel. I don't know what he's doing now. Anyways. All right. And here's a Blue Angel back when they were still flying, I think, A4s. Now they fly F-18s. Not that that means anything to any of you. But anyway. All right. Well, I just know that's a picture of an A4. That's not an F-14. All right. Okay. The object, oh, the virtual image is diminished in size and upright. So every time with the convex mirror, there you go. All right, let's talk about the lens equation, and then I'm going to stop the laser light show, and we're just going to work some examples. Have y'all followed this pretty well? Yeah, it's all pretty straightforward. It's nice slides. I think the slides go nicely. Okay, so you got a focal length. All right, first of all, tell me what the focal length is. What's it equal to? What's that? 1/2 R. Yeah, it's 1/2 R. It is 1/2 the distance. What is R? Radius of curvature of the mirror. Okay, what if I've got a convex mirror? What happens to my focal length? It's negative. Right. All right, good. Okay, DO is the distance of the object. DI is the image distance. And M is the magnification. You all probably used the now this is, you've all seen this already. This was with your lab. They might have used different variables. I don't know why they would do that, but because I saw some work from some people, and yeah, they used X and Y. I don't know. That kind of made me mad, but because DO makes sense to me. Distance of object, distance of image. Okay. Now, think about what you've learned so far. The object distance is always going to be positive because that's always going to be in our real world. Okay? What happens? What would happen? Would you be able to tell me what kind of mirror it is if the image distance was negative, if DI was negative? Your first idea is it'd be convex because I know they're all virtual. However, didn't we have a concave mirror where the virtual image, where it also had a virtual image? So anytime you got a virtual image, the distance of the image, virtual, negative. Okay? Because virtual means he's in Alice's world, not in the real world. Okay? So he's negative. But if they said, let's take an example. Let's say the magnification. Oh, we'll get to it in a minute. Sorry. I was getting ahead of myself. Okay. And magnification. Magnification means how big it is. Here's the thing, though, that trips people up when they're first studying optics. Let's say something is -2. The magnification is -2. Magnification is just a number. Does that mean the object is smaller or twice as big and just upside down? Twice as big and upside down. That's what magnification -2 means. Okay? It means that the image is twice as big and just upside down. All right? But if you get a magnification of 0.4, that means it's shrunk and it's still upright. Okay? It's shrunk and it's still upright. If you get a negative magnification, that means it's inverted the image, the object. It's inverted the object. Okay, those are all the little tricks of the trade that we'll get to. And here we go. Do you want to go through the proof of it? No, not when it's 79 degrees outside on July, 17th, and we got a beautiful San Diego type day. No way are we going to go through the proof of it. You're just going to believe it, right? That 1 over F equals 1 over DO plus 1 over DI. Okay? 1 over F. And the magnification, which this magnification makes sense to me. Height of the image divided by the height of the object. Okay, well that makes sense. But it's also, you can also use this one. And Naomi learned this one Monday or Wednesday so that she could complete the lab because she was going, wait a minute. They were messing with you somehow. I can't remember what they were doing. But they basically they gave you one equation and 2 unknowns and they told you to find the solution. There's no way to do it. Here's the second equation that they forgot to tell you about. DI over DO. But it's a negative. So I always to keep myself, when I do these problems, I always put my DI in parentheses. Because if my DI turns out to be negative, in other words, if it's a virtual image, in Alice's world, if it's the Queen of Hearts or whatever, then this negative over negative means it's going to be positive. Okay? Which makes sense because our magnification says it's supposed to be upright. Okay? Whether or not it's going to be bigger, we don't know. Okay, so let's just do it. Now, here's what we did. Here's the way I teach this chapter every time, and it seems to work. Now we're going to do examples. Okay? In your homework, we might even do a couple homework problems. So we've done chapter 25. So that means I can start 26. So that means your take-home will cover chapters 23, 24, 25, 26. Kidding. It'll cover chapters 24 and 25. Maybe a little bit of 26. I don't know. Because 26 is pretty important too. Oh, that's on. What am I missing? Oh, I got to turn this off. Okay. Let's do some examples. Let's do an example. Let's do a homework problem. Those are always fun. Uh-oh. I forgot my glasses. That's okay. And we'll get into that too. On how glasses work. why my cornea. And by the way, what does your any future optometrists here? No future optometrists or ophthalmologists or anything like that? Okay. Anyway, what was I going to say? Something important. Not now. The image in your brain. Is it upright or upside down? It's upside down. But your brain goes, I know what you mean. Okay. It's kind of one of those weird things. Okay, now, let's take a look at problem number 8. I think I assigned problem number 8 because I always assign problem number 8. And then every semester invariably, because I like the problem, I wind up doing it anyway, so I don't know what you get out of it. I just like doing it. Okay, it says 2 plane mirrors. Here we go. We've got 2 plane mirrors. They're not fancy mirrors, they're plane mirrors. Oh boy. All right, now, they're like this, okay? And they're facing each other like that. And then there's 17, the other beautiful thing about mirrors, if it says centimeters, stay in centimeters. You don't need to convert anything. It's just straight geometry, okay? They're both 17 centimeters long, okay? And they're separated by 3, the separation here is 3 centimeters. Okay. By that. So far, so good. Okay, now what I'm going to do is I'm going to shoot a little laser beam of light. This, boink, here's my little laser beam of light. And I want it to come out of here just like that. I want it to get reflected only once. Okay? And okay? Now, I want it to hit just that mirror once. What's the smallest angle of incidence that I can have? In other words, you could say, well, shoot, you've got a whole range. You could go all the way, you could put it all the way down here so it hits here and goes like that, or hits here and goes like that. But we want it so it just whoosh, goes out like that. Okay? So how would we do this? First of all, theta I equals theta R. Okay, theta I equals theta R. All right. Now let's do a little geometry. First of all, we could actually use the law of sines, but I don't want to. No, because I don't know what these 2 lengths are. But I've actually probably developed a isosceles triangle. Let's go ahead and do this. Let's drop this angle of incidence here. Okay? There's my angle of incidence. And by the way, it is perpendicular here. And I have, and it cuts this in half. So I know that this is 8.5 and this is 3.0. Because this angle, theta I, has to equal theta R. Those two are the same. So I've made two. So this phi is equal to this phi over here. Basically, I got two congruent triangles. Oh! Tangent of what? Tangent of phi? Yeah.
Like inverse tangent.
Exactly. Of phi, right? This guy? Yeah. Perfect. That's it. Class dismissed. That'll work. I was going to go into something really hard, but then Catherine goes, hey, wait a minute. Look, you got yourself the tangent of phi here. Equals 3 over 8.5. So you take phi equals the inverse tangent of 3 over 8.5. Man, a Wiley plus, you're going to get different numbers. Make it harder. Same damn thing. Be all right. Okay. Now. All right. But I'm not going to do the second part for you. The second part says it has to hit each mirror only once. So the second part is going to be this. It's going to go boink, 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 like that. Ooh. Now it's harder. But wait a minute. What if I do this? These two are the same. Oh, look at that. A, and A, they're all the same. There's my hint. All right.
How do you know for sure that line cuts it directly?
Cuts what directly in half?
Mirror length exactly in half.
Oh, because we're actually trying to get it to be right here. So I've got theta I equals theta R, right? And so therefore, and it's going across the normal. And the normal of this bisects the base of an isosceles triangle. Thales theorem. Maybe, I think. Could be. This is being broadcast to millions. Anybody out there in TV land? I think it's Thales theorem. All right. So, if not, cards and letters to the provost. Okay. Let's do some mirror equation things. All right, let's do some mirror equations. Let's do a convex and a concave mirror. Let's do a convex and a concave mirror. I'm going to look at problem 17 and 18 here. We'll look at problem 17 and 18. And then we probably should pretty much are done, because we'll have done a concave and a convex mirror. And so these are pretty good. Everything we're going to do with the lens and the mirrors comes from that. All right, now, here we go. Problem 17 says this. The image behind a convex mirror. Okay, so here I got a convex mirror. And the image behind it, first of all, the image behind it is going to be what? It's going to be virtual, and it's going to be upright and smaller, right? And, okay, David was saying negative. You're talking about the distance, the DI is going to be negative. You're absolutely right. DI will be negative. So I've got a DO out here. Okay. It says here that I've got the image behind is located 22 centimeters from the mirror. Okay, so this is 22 centimeters from the mirror. The radius of curvature is 68. Radius of curvature is 68 centimeters. So therefore, my focal length is what? What would be my focal length? Negative 34. Right, negative 34. F is negative 34 centimeters. Let's see, what didn't they give me? I'm just guessing. I haven't read the whole problem all the way through. I bet we have to come up with DO and the magnification. It says, where is the object located? Yep. And what is the magnification? Yep. And determine whether the image is upright, inverted, and D larger or smaller than the object. Boom, we got a lot to do. But it'll all spill out real simply. Because of this, all we have to do is this. 1 over F equals 1 over DO plus 1 over DI. And we have to be very, very careful. I'm hunting rabbits. No. We got to be very, very careful about where we put our negatives. Okay? So we go 1 over negative 34 equals 1 over DO plus 1 over negative 22. Okay, now to solve this, I'm going to have to add 1 over 22 to both sides. Will this make sense? There we go. And I forgot to bring my calculator. But here's the way I do these. Here's the way I do these. I do them like this. I just go 1 divided by 22 minus parentheses 1 divided by 34, close the parentheses, press enter. I got this screwy thing, and then I hit x to the negative 1. Hit your x to the negative 1 key, enter, 62.3. So DO will equal 62.3 centimeters, which makes sense because it is a because the distance of the object should be positive. Okay? I can double check that answer. This is scary. I did an odd one. I usually like to do even ones so that you can't double check on me. All right. 17. Yes! All right, now let's get the magnification. Let's get the magnification. M is equal to HI or HO, or the negative DI over, negative DI over DO. So for this case, you've got to be very careful. You've got to go M equals negative, then DI always put, I'm going to put my DI, which is right here, in parentheses, divided by 62, negative, negative, it's about 1/3. I'm going to call it 1/3. Close enough, right? I think their answer was 0.36. Yeah. Plus or minus 9% on Wiley Plus. We'll take it. Okay. All right. One more problem. One more problem. Then we're going to go jog around Loose Park. It'll be a nice day. I have to watch out for the yuppie moms with their strollers, though. You don't want to get too close to Poindexter there. You get a latte thrown on you. All right. Anyway, sorry. Not to stereotype the Brooksiders. But sorry, didn't mean to breathe on him. Yes, I'm sure he's going to Harvard. All right. Little baby Mozart there. Good. You know it's been proven to not be effective. Oh well. Anyway, How much does Grandpa make? That depends on where he's going to go to school. All right. Oh boy, we got off track here. Okay, it's problem 18. I got to thinking about running around bricks. A concave mirror. The concave mirror has a focal length of 12 centimeters. F equals 12. Okay, we're doing concave. Equals 12 centimeters. This mirror forms an image located 36 centimeters in front of the mirror. Okay, the distance of the image is positive 36 centimeters. I wonder what they're going to ask. What is the magnification? Oh, they want to know M. I knew I'd find a good marker by the time class was over. There we go. We want to find M. Well, we've got to find DO first. Then we can find M. All of these are about every time you're either going to find the focal length, or you're going to have to find the DI, or we're going to find the magnification. First of all, we know it's concave because DI is positive. The focal length is also positive. So we do this. We go 1 over DO. Oh, it looks like this one actually has fractions I can work with. I might not need to borrow Jared's calculator here. 1 plus 1 over 36 equals 1 over 12. Okay, so I've got 1 over DO plus 1 over 36. Well, why are you writing the same thing twice? Because I was thinking. 1 over 12 minus 1 over 36. This is a good thing because it's going to turn out to be nice and positive. Okay? And this equals, well, I can turn this into what? 3/36? Isn't that right? 3 over 36 minus 1 over 36 equals 2 over 36. Now remember, this is your 1 over DO, so you're going to have to flip it over. So you get 36 over 2, and so DO equals 18 centimeters. All right, so this is one of those ones that was kind of strange. The distance of the image is behind, the image is actually behind the object. And it's probably upside down and bigger. Let's check and see. So we want the magnification is equal to negative DI over DO. So DI was what? 36 over, I'm going to go ahead and put it in parentheses just because I get in the habit of doing that so I don't screw up that negative sign. Negative, that's DI, right? What's DO? 18? Oh, look, it's twice as big. M equals negative 2. And there's no units with magnification. It's unitless. But this tells me that the image is twice as tall and upside down. And this tells me that the image is actually behind the object. Kind of strange. It's the old spoon thing. Mirrors, they're pretty easy. It's nice and straightforward. The strange thing, there's a little break. The first 25 chapters you learn, this is kind of a nice and easy one. Good old geometry and fractions, fraction algebra. That's it.